The origins of evolutionary thought can be found as early as 500 BC in ancient Greece. Ancient pre-Socratic philosophers like Thales, Xenophanes, and Herodotus were not far off given their limited resources. Thales pondered the origins of life and created the first recorded natural explanation, which stated that all life came from water. Xenophanes and Herodotus were the first humans to recognize fossils as the remains of living creatures. Based on the distribution of marine fossils, the two philosophers speculated that the lands had been formerly covered by the ocean. Philosophers like Plato, Aristotle, and Hippocrates debated various theories and explanations of life up until the medieval times. During the medieval era, natural theology took over and adopted Aristotle's theory of perfect creation. Natural theology slowly began to lose its grasp on people's perceptions during the Enlightenment. Perhaps the beginning of this transformation was marked by Andreas Versailles, a young anatomist. Until Versailles, European scholars had relied on Galen for all their anatomical information. The universities at the time had blindly accepted Galen's work. Professors would read Galen to their students while a surgeon would dissect a criminal in front of them. The professor would never look at the body for himself because everything worth learning was already written in Galen's books. Once Versailles started to dissect bodies for himself, he found that Galen was drastically wrong. Galen had never gotten the chance to dissect a human because the laws in Rome at the time didn't allow for such practices. Instead, Galen was limited to evidence from dissecting other animals and the surgeries he performed on his patients. Versailles published his work in his book called the Fabrica. In the Fabrica, Versailles pointed out the important similarities and differences between humans and animals. Versailles' discoveries helped pave the way for comparative anatomy, where researchers study the differences between humans and animals. After comparative anatomy was introduced into the sciences, researchers began to view humans as one species among many. 300 years later, Darwin would use comparative anatomical knowledge as a key part in his theory of evolution. The next great step forward in the history of evolutionary thought was the birth of paleontology. In 1666, two fishermen caught a giant shark off the coast of Livorno, Italy. Niels Stenson, also known as Steno, dissected the shark and was surprised by how similar they were to what people called tungstones. People today would view these stones as petrified shark teeth, but at the time such a presumption would have been a huge leap of thought. Steno eventually developed theories explaining how living material like shark teeth could be turned into stone. Steno also created the law of superposition, which explained how fossils end up deep inside rocks. One of the key elements of the law of superposition was that the oldest fossils were furthest deep, while more recent ones were closer to the surface. Steno pushed his theories further, arguing that fossils were snapshots of life at different moments in history. Steno led the way for fossils to be used as key evidence in explaining how life evolved on Earth. Jean-Baptiste Lamarck was also a key figure in the development of evolutionary theory. Lamarck's studies of animals and fossils led him to believe that life was not fixed. Lamarck argued that when environments change, organisms have to change their behavior to survive. A giraffe would stretch its neck to reach taller trees. Then the giraffe's elongated neck would be passed on to its offspring. Lamarck also proposed that organisms were driven from simple to complex. Lamarck's envisioning of evolutionary change was a new hypothesis at the time. Though Lamarck may have made many mistakes, he helped pave the way for Darwin. Darwin used much of the same evidence that Lamarck used. Evolutionary theories like Lamarck's had been promoted prior to Darwin. However, when attempting to explain how life changed, these theories relied on speculation. Much of Darwin's work was simply unifying all the evidence that had previously been discovered into one theory. Darwin drew his inspiration from economics. While Darwin was reading Essay on the Principle of Population by Thomas Malthus, It had occurred to him that the same population pressures humans face were applicable to animals as well. Darwin reasoned that in this environment, traits which help the animal breed or survive more successfully would leave the animal with more offspring than others. As time went by, this trait would become more and more common in following generations, given that it still provides the animal survival or breeding advantages. Darwin took 20 years to complete his book on the origin of species. During this time, Darwin collaborated briefly with Wallace, another biologist whose work was on a similar theory. Wallace decided to seek help from Darwin in publishing his own theories. After reading Wallace's theories, Darwin was shocked to find that Wallace's theories almost completely replicated his own. Darwin's book on the origins of species was probably one of the most influential books of all time. The science community was not receptive to Darwin's ideas at first, but after a couple of decades, most scientists adopted the theory. However, during the late 1800s, most scientists who accepted evolution still preferred the Lamarckian explanation for the way of life evolving over time. It was not until the 20th century that natural selection as an explanation would gain full traction. Throughout the 19th century, Darwin, along with many other scientists, were puzzled over heredity. How was it that children look like their parents? The answer to this question lies at the heart of evolution. Gregor Mendel was the first one to get a glimpse of the biological mechanism behind heredity. Mendel learned how to analyze data and design experiments at the University of Vienna. In Mendel's experiment, he selected 22 different types of peas and interbreeded them. After observing the pea traits through multiple generations, Mendel concluded that when wrinkled and smooth peas breed, their offspring inherits both traits, but only the smooth trait becomes visible. In the next generation, a quarter of the peas would inherit 2 wrinkled traits, which would cause these peas to be wrinkled. Mendel had discovered what scientists now call dominant and recessive alleles. Unfortunately, Mendel could not stir up any interest in his results for two reasons. First, scientists at the time did not apply statistics to natural history, and second, Mendel failed when he tried to replicate his results with hawkweed. The reason Mendel could not replicate his results with hawkweed was because of the plant's unusual genetics. 15 years after Mendel's death, scientists began to realize his work was the answer to the puzzle of heredity.